The cosmos is a magnificent illusion. Every star, every planet, every particle of dust you can see is just a tiny fraction of what truly exists. Beneath the surface of reality lies an invisible framework, a hidden architecture of forces and fields that dictate everything from the weight of an atom to the fate of the entire universe. By the end of this journey, you will understand 30 mind-bending theories about these hidden fields, from the firmly established to the wildly speculative. What if gravity is not a force but the curvature of an unseen fabric? Could a secret field be responsible for your own consciousness? We are about to dive into the deepest layers of existence, exploring the ideas that define our cosmos. What do you think is the most profound secret the universe is keeping from us? Our journey begins with the most famous of all hidden fields, one that has been experimentally confirmed. This is the Higgs field. Think of the entire universe not as empty space but as an ocean. Now imagine this ocean is filled not with water but with a strange, invisible molasses. This is the essence of the Higgs field. It is not made of matter, but it is everywhere, a fundamental property of the vacuum of space itself. As particles move through this cosmic molasses, they interact with it. Some particles, like photons, which are particles of light, zip right through without a care. They feel no drag, and so they remain massless, traveling at the ultimate speed limit of the universe. But other particles, like quarks and electrons, get bogged down. They interact strongly with this sticky field, and that interaction is what we perceive as mass. The more a particle struggles against this molasses, the heavier it is. So, the mass of everything around you, from the chair you are sitting on to the very atoms in your body, is not an intrinsic property. It is a gift from this omnipresent hidden field. For decades, the Higgs field was just a brilliant piece of theoretical mathematics, a crucial but missing part of the puzzle explaining how the universe works. The hunt to prove its existence became one of the greatest scientific endeavors in history, centered on a machine of almost unimaginable scale. Deep beneath the border of France and Switzerland, scientists at CERN built the Large Hadron Collider, a 17-mile ring where protons are smashed together at nearly the speed of light. They were not looking for the field directly, as you cannot see the molasses itself. Instead, they were searching for its signature, a ripple in the field. Just as throwing a stone into a pond creates a splash, a tremendous collision of energy in the vacuum can create a brief, detectable excitation of the Higgs field. This excitation is a particle, the Higgs boson. In 2012, after analyzing trillions of collisions, scientists announced they had found it. That tiny, fleeting particle was the proof. The molasses was real. The discovery of the Higgs field was a monumental moment. It was the first time humanity had ever directly confirmed the existence of such a fundamental, invisible scaffold of reality. It validated a half-century of theoretical work and completed our standard model of particle physics. But more importantly, it opened the door. It proved that the vacuum of space is not nothing. It is a dynamic, active medium filled with hidden fields that dictate the rules of existence. If one such field exists and gives particles mass, what other fields are out there waiting to be discovered? What other fundamental properties of our universe are not features of matter, but whispers from the hidden architecture of empty space itself? The Higgs field was not the end of the story. It was the very beginning, showing us exactly where to look next. The discovery of the Higgs field revealed a profound truth about our universe. It showed us that the bedrock of reality is not a collection of tiny, solid balls, but something far more fluid and strange. This leads us to our second theory, the grand framework that houses the Higgs. This is quantum field theory, and it is the single most successful scientific theory ever devised. It paints a picture of a universe that is never truly empty or still. Instead, the entire cosmos is a churning, bubbling sea of invisible fields. There is not just one Higgs field. There is an electron field, a quark field, a photon field. Every fundamental particle we know is not a distinct object but a tiny knot of energy, a localized vibration in its corresponding field. Think of it like a vast, calm lake stretching to infinity. That calm surface represents the field in its lowest energy state. Now toss a single pebble. The ripple that spreads out is not the lake itself, but a disturbance in it. That ripple is a particle. An electron is a ripple in the universal electron field. A photon is a ripple in the photon field. These fields are not made of anything else. They are the fundamental ingredients of existence, and particles are simply how these fields express themselves when given energy. This framework is the engine of the standard model of particle physics. It elegantly describes three of the four fundamental forces of nature. The electromagnetic force is carried by ripples in the photon field. The strong nuclear force, which glues atomic nuclei together, is mediated by ripples in the gluon field. The weak nuclear force, responsible for radioactive decay, involves the W and Z boson fields. Every interaction, every chemical reaction, every flicker of starlight is ultimately the result of these hidden fields conversing with one another, their ripples intersecting and exchanging energy. The success of this theory is staggering. Its predictions have been confirmed to an almost unbelievable precision, matching experimental results to many decimal places. It explains nearly everything we see in the world of the very small. Yet, for all its power, quantum field theory is not the final answer. It leaves glaring, monumental mysteries unsolved. The most famous of these is gravity. Our theory of gravity, Einstein's magnificent general relativity, describes the cosmos as a dynamic, flexible fabric of space and time. It works perfectly for planets, stars, and galaxies, but we have no idea how to make it talk to the quantum world of fields and ripples. Gravity stubbornly refuses to be woven into the same tapestry. This means our universe currently operates under two rulebooks, one for the very large and one for the very small, and they are written in completely different languages. This conflict points to a deeper layer of reality, a hidden field or a new principle that might finally unite them. What could possibly be powerful enough to bridge the gap between the tiny world of quantum ripples and the vast curvature of cosmic spacetime? Gravity's stubborn refusal to join the quantum party is not the only mystery. Our cosmic story has an even bigger plot hole right at its very beginning. The Big Bang Theory tells us the universe exploded from an unimaginably hot, dense point. But when we look at the sky with our most powerful telescopes, we find details that this simple explosion cannot explain. Why is the universe so incredibly uniform? Look in any direction, and the distant cosmos looks almost exactly the same, with the same temperature and distribution of galaxies. This is bizarre. In the standard Big Bang model, there was not enough time for light, let alone heat, to travel across the universe to smooth everything out. It is like walking into a vast auditorium and finding every single seat at the exact same temperature, even though the heaters on opposite walls have never had time to communicate. This is called the horizon problem. Furthermore, the geometry of our universe appears to be perfectly flat, balanced on a knife's edge between eternal expansion and catastrophic collapse. The odds of this happening by chance from a chaotic birth are astronomically small. This is the flatness problem. To solve these puzzles, scientists proposed a radical idea, a cosmic plot twist that occurred in the first fleeting moments. They introduced a new hidden field, the inflaton field. Picture the newborn universe smaller than a subatomic particle, seething with unimaginable energy. In this realm, the inflaton field was trapped in a state of false vacuum, a condition of incredibly high energy that acted like a cosmic battery. This state had a peculiar property. It exerted a tremendous negative pressure, a kind of repulsive gravity. And for a sliver of time so brief it defies comprehension, perhaps only a trillionth of a trillionth of a trillionth of a second, this field dominated everything. It caused space itself to expand not just rapidly but exponentially. The universe did not simply grow, it doubled in size and then doubled again and again, over 60 times or more. In that instant, a region smaller than a proton was stretched to a size larger than our entire observable universe today. This solves the horizon problem instantly, because everything we see was once crammed into a tiny, connected quantum region that had plenty of time to even out before being blown apart. It also solves the flatness problem, because this hyper-stretching would smooth out any curvature, like blowing up a wrinkled balloon to make its surface appear perfectly flat. Then the story reaches its climax. The inflaton field was unstable. Like a ball perched on the peak of a hill, it could not stay in that high-energy state forever. It decayed, tumbling down to its lowest, calmest energy level. But all that colossal energy stored in the field had to go somewhere. It did not simply vanish. As the inflaton field decayed, it dumped all of its pent-up energy into the fabric of space, reheating it into a roaring, dense soup of particles and radiation. This was the true beginning of the hot Big Bang we talk about. The Big Bang was not the first moment, it was the aftermath. The inflaton field was the engine, the explosive catalyst that set the stage for everything to come. We have not detected this field directly, but its predicted fingerprints, the specific patterns of temperature variations in the cosmic microwave background, match our observations with stunning accuracy. So we are left with a profound implication. The entire universe we inhabit, hundreds of billions of galaxies, each with hundreds of billions of stars, may be the result of a single quantum fluctuation in a hidden field that briefly held the keys to creation itself. If a field could orchestrate this, what other primordial fields might have left their mark on the cosmos, quietly shaping its destiny from the shadows? That inflationary burst set the universe in motion, but the story of cosmic expansion was far from over. For most of cosmic history, gravity was the dominant force, slowly pulling the universe back together against its initial outward momentum. Then, around 5 billion years ago, astronomers made a discovery that shattered this assumption. They found that the expansion of the universe is not slowing down. It is speeding up. Something is actively pushing galaxies apart, a mysterious repulsive force woven into the fabric of space itself. We call this phenomenon dark energy. The simplest explanation is Einstein's cosmological constant, a fixed property of empty space that gives it a kind of inherent, unchanging stretch. But what if dark energy is not a constant at all? What if it is a dynamic, living entity? This brings us to our fourth theory, the idea of quintessence. Quintessence is not a number in an equation. It is a hidden field, a cosmic cousin to the inflaton field that drove the Big Bang. Like the inflaton, quintessence is thought to permeate all of space, a kind of energy fluid with its own unique properties. But while the inflaton field acted in a blinding flash at the beginning of time, quintessence operates on a timescale of billions of years, its influence growing as the universe ages. The key difference is in how its energy behaves. Imagine a ball rolling down a very gentle, almost flat hill. The cosmological constant is like that ball coming to rest at the very bottom, in a state of perfect, unchanging equilibrium. Its energy density never changes. Quintessence, however, is like a ball that is still rolling. It is evolving. The shape of its hill, what physicists call its potential, is changing over cosmic time. This means the energy density and pressure of the quintessence field can change as well. Right now, its negative pressure is driving the acceleration we observe, gently pushing the cosmic fabric apart. But in the future, that could change. The field could decay, causing the acceleration to stop or even reverse, or more dramatically, it could strengthen. This leads to a possible cosmic fate far more violent than a slow fade. If the quintessence field's repulsive power grows stronger over time, it would not just push galaxies apart. First, it would tear galaxy clusters from one another. Then, as the force intensifies, it would rip individual galaxies apart, stars flung into the endless dark. Later, planetary systems would be shredded. In the final moments, even atoms and atomic nuclei would be torn asunder by the overwhelming stretch of space itself. This apocalyptic scenario is known as the Big Rip. While this is a speculative extreme, it illustrates the profound implications of a dynamic dark energy field. A static cosmological constant is simple, but quintessence is a story. It has a past, a present, and a future that could rewrite the ultimate destiny of everything. The hunt is now on to distinguish between these possibilities. Astronomers are meticulously measuring the expansion rate across cosmic history, searching for any tiny variation that would signal the rolling ball of quintessence. They are looking for the fingerprint of a field in motion. If they find it, it would mean the universe is not just expanding, it is breathing, driven by a hidden rhythm we are only beginning to sense. Dark energy might dictate the fate of cosmic expansion, but another hidden field could be responsible for the very structure of the cosmos. While dark energy pushes, dark matter pulls. This invisible substance, which makes up about 85% of all matter in the universe, does not emit or absorb light, yet its gravitational grip is the only thing holding galaxies together. For decades, the leading candidate for dark matter has been a hypothetical heavy particle, a weakly interacting massive particle, but despite exhaustive searches, we have found nothing. This failure has led physicists to consider a radically different possibility, one born not from a problem of missing mass, but from a profound puzzle in the laws of physics itself. This is the action field. The mystery it solves is called the strong CP problem. It concerns the strong nuclear force, the incredibly powerful glue that holds quarks together inside protons and neutrons. Our equations allow for this force to violate a symmetry known as CP, which would make the neutron have a tiny electric dipole moment, a sort of internal north-south charge separation. If this were true, it would have dramatic consequences, making atoms unstable and chemistry as we know it impossible. Yet, when we measure neutrons with exquisite precision, we find no such electric dipole moment. The symmetry is perfectly preserved. The laws seem to be fine-tuned to an astonishing degree, and physicists hate fine-tuning without a reason. The action field provides an elegant solution. It proposes a new, universe-filling field that, in the earliest moments after the Big Bang, naturally settled into a state that cancels out this problematic CP violation. The adjustment is automatic and beautiful, but like the Higgs field settling down and releasing the Higgs boson, the action field, as it relaxed to its lowest energy, would have generated ripples. These ripples are actions, extremely light, ghostly particles that interact with ordinary matter only incredibly weakly. They are not the heavy bullets we imagine for dark matter, but something more ethereal. Trillions of them could be passing through your body every second, and you would never feel a thing. This is where the story converges with our cosmic mystery. In the hot, dense early universe, a vast number of these actions would have been produced. Because they are so light and non-interactive, they would not have clumped together in the way ordinary matter does. Instead, they would form a colossal, diffuse cloud, a wave-like halo enveloping every galaxy. This halo would not have a sharp edge. It would be a gradual, shimmering field of quantum waves with a density that peaks at the galactic center and fades out into the void. This matches the gravitational effects we observe from dark matter perfectly, the invisible scaffold that guides the motion of stars within galaxies. The hunt for actions is a testament to human ingenuity, requiring not giant colliders but exquisitely sensitive listening posts. The most famous experiment is called a DMX, the Action Dark Matter E experiment. It operates on a principle akin to a cosmic radio receiver. Scientists theorize that in the presence of a tremendously strong magnetic field, an action could very rarely convert into a photon, a particle of light. The DMX apparatus is essentially a supercooled, tunable radio cavity sitting inside a powerful magnet. The idea is to tune this cavity through millions of possible frequencies, listening for the faint whisper of an action converting into a microwave photon within the chamber. It is like searching for one specific silent station on a radio dial with an infinite number of channels, hoping to hear a single, perfect note emerge from the static of the universe. Laboratories around the world are engaged in this delicate hunt, refining their instruments to hear the signature of a field that may have saved the laws of physics and, in doing so, built the invisible skeleton of the cosmos. If they succeed, it would solve two profound mysteries with one elegant, hidden whisper from the vacuum. The action hunt is a delicate search for a ghost, but what if the hidden field we seek is not just shy but actively hiding from us? This brings us to a theory so clever it seems almost mischievous, the idea of chameleon fields. Imagine a force of nature that is not constant but context-aware. In the vast, near-empty expanses between galaxies, this hypothetical field would be light and wispy, its influence stretching over cosmic distances, gently shaping the large-scale structure of the universe. It could even be a candidate for dark energy itself, but bring this field into a dense environment like our planet or a laboratory experiment, and something extraordinary happens. It changes. The field senses the high density of ordinary matter around it, and like a chameleon shifting its color to match the leaves, it alters its fundamental properties. In these crowded spaces, the field becomes incredibly massive and heavy. This massiveness confines its influence to an extremely short range, perhaps smaller than the width of a human hair. In a laboratory, its effects would be virtually undetectable, hidden behind a wall of its own making. This is not a flaw in the theory, it is the whole point. The chameleon mechanism is a brilliant proposed solution to one of the biggest puzzles in modern physics, why we have not found a fifth fundamental force. For decades, theorists have suggested that beyond gravity, electromagnetism, and the nuclear forces, there could be additional forces mediated by new hidden fields. These would manifest as subtle tweaks to gravity or new interactions between particles. Yet, despite our most sensitive experiments, we see no sign of them. The chameleon field explains this absence perfectly. Our detectors are all here on Earth, a region flooded with matter. If the field is a chameleon, it has gone into hiding right where we are looking, becoming so short-ranged and weak that it seamlessly blends into the background noise of known physics. To find it, we would need to look where it feels safe to reveal itself, in the vacuum of space. Scientists are already designing missions to do exactly that. Proposals involve sending exquisitely sensitive instruments into orbit, where they can measure the force between two test masses in the pristine quiet of microgravity. In that near-perfect vacuum far from Earth's dense matter, the chameleon field might finally drop its disguise, showing its true, light, long-range nature. It is a cosmic game of hide and seek where the playing field itself changes the rules. The very idea challenges our intuition about the constancy of physical laws, suggesting that the fabric of reality might be more adaptive, more responsive to its environment than we ever dreamed. If such a field exists, it would mean the universe possesses a kind of ambient intelligence, a hidden layer that modifies its own behavior based on context, forever eluding our grasp until we learn to look in the right place under the right conditions. The chameleon field is a master of disguise, but it is not the only hidden actor that knows how to vanish in a crowd. Another contender in this cosmic game of hide and seek is the symmetron field, a concept that ties the fate of a hidden force to one of the most profound ideas in physics, symmetry breaking. To understand this, picture a simple, everyday object, a pencil balanced perfectly on its tip. In that precarious position, the pencil is symmetrical. It looks the same from every horizontal direction, but this symmetry is unstable. The slightest breath of air, the tiniest vibration, will cause it to fall. When it does, it points in one specific, random direction. The perfect circular symmetry is broken. The symmetron field operates on a cosmic scale, but with a similar principle. In its natural state, throughout most of the universe, this field has a value of 0. It is dormant, inactive, and perfectly symmetrical. But this symmetry, like the pencil on its tip, is fragile. It is held in place by the density of matter surrounding it. In the vast, near-empty voids between galaxies where matter is incredibly sparse, the grip of this density weakens. Past a certain threshold, the symmetron field can no longer maintain its symmetrical 0 value. It spontaneously acquires a non-zero value, a specific orientation, just like the pencil choosing a direction to fall. In that moment, the symmetry is broken and the field wakes up. It turns on. Now, here is the crucial twist. When the symmetron field has a non-zero value, it can mediate a new force, a subtle fifth force that could gently tug on matter. But in regions of high density, like within a galaxy or here on Earth, the overwhelming presence of matter forces the field back to 0. It is suppressed, switched off. Its force simply does not exist in our local neighborhood. This is why we have never detected it. We are living in a cosmic metropolis where the symmetron field is permanently asleep. Its effects would only be visible out in the wilderness, in the great cosmic voids where galaxies are few and far between. This makes the symmetron a fascinating candidate for dark energy. If this field has a non-zero value in the voids, its energy could permeate those empty spaces, contributing to the repulsive push that drives the universe apart. But its potential goes further. The fifth force it produces in the voids could subtly influence the distribution of the sparse matter that does exist there, perhaps causing galaxies at the edges of voids to align in peculiar ways or move with unexpected speeds. Astronomers are now scanning these immense, dark deserts of space, looking for any anomalous gravitational lensing or strange galaxy flows that cannot be explained by ordinary matter and gravity alone. They are searching for the ghostly fingerprint of a field that only stirs in the deepest emptiness, a force that emerges from the silence. It suggests a universe where the laws of physics are not uniform but conditional, changing their character based on the emptiness or fullness of space itself. What other rules of reality might be quietly suspended, waiting for us to look in the right, lonely place? The symmetron's conditional nature hints at a universe of hidden variables, but there is one field we know is real, one that defines the very stage upon which all others play. This is the gravitational field, but to call it a field in the traditional sense is almost a misnomer. In Einstein's revolutionary vision, gravity is not a force that pulls. It is geometry. The presence of energy and matter from a single atom to a massive star warps the fabric of spacetime around it. This warping is the gravitational field. Think of a taut, flat rubber sheet representing empty space. Place a heavy bowling ball in the center, and it creates a deep, curved dent. Now roll a marble across the sheet. It will not travel in a straight line. It will spiral inward, tracing a path along the curved geometry created by the bowling ball. The marble is not being pulled by a mysterious force. It is simply following the shortest path through a bent landscape. Earth orbits the Sun not because it is tugged by an invisible rope, but because it is rolling along the curved groove the Sun's mass creates in the cosmic fabric. This elegant idea, called geometrodynamics, is the core of general relativity. It has passed every test with flying colors, predicting the precise bending of starlight around the Sun and the subtle wobble of Mercury's orbit. Its most dramatic confirmation came just a few years ago, not with a static image, but with a ripple in that very fabric. When two massive objects like black holes spiral together and collide, they do not just shake the space around them. They send tremors through spacetime itself, stretching and squeezing it as they pass. These are gravitational waves. In 2015, the LIGO Observatory detected the faint whisper of such a collision over 1 billion light-years away. The signal perfectly matched Einstein's predictions. For the first time, we literally heard the gravitational field ringing like a bell. Yet, for all its success, this geometric picture of gravity faces a profound crisis when it meets the quantum world. In quantum field theory, every force is transmitted by particles. The electromagnetic force is carried by photons, the strong force by gluons. So, what carries the gravitational force? The hypothetical answer is the graviton, a massless particle that would be a quantum ripple in the gravitational field, just as a photon is a ripple in the electromagnetic field. But here, the mathematics breaks down catastrophically. When you try to calculate simple interactions involving gravitons using the standard rules of quantum mechanics, the equations spit out infinities that cannot be reconciled or removed. The smoother, continuous geometry of general relativity seems fundamentally incompatible with the grainy, probabilistic nature of the quantum realm. This is the central problem of modern physics. The gravitational field, as we understand it, interacts with everything that has energy. It is the ultimate democratic force, bending the path of light just as it guides planets. But its quantum nature remains a locked door. Some theories suggest the answer lies not in particles, but in the fundamental threads of spacetime itself, that the field is woven from something even more basic. Until we solve this, our understanding of the universe's hidden architecture is incomplete, missing the instructions for how its most fundamental stage is built. Einstein's spacetime was a smooth, curving fabric, but what if that fabric could also twist? Our geometric picture of gravity might be missing a crucial dimension, one tied to the very quantum nature of matter. This brings us to a fascinating extension of general relativity, the Einstein-Cartan theory. In this framework, spacetime is not just curved by mass and energy, it can also possess torsion. Think of the difference between bending a sheet of paper and twisting a corkscrew. General relativity describes the bend, the graceful dip created by a planet or star. Torsion describes a microscopic spiraling, a corkscrew-like twist in the very threads of spacetime. And the source of this twist is not mass, but something purely quantum, the intrinsic spin of fundamental particles. Every electron, every quark spins like a tiny top. In Einstein-Cartan theory, this spin does not just exist within spacetime, it actively imparts a twist to spacetime itself. The density of spinning matter in a region creates a torsion field, a hidden geometric property that adds a new layer to the gravitational interaction. For most of the universe today, this effect is vanishingly small. The spin of particles is random and cancels out on large scales, like countless tiny corkscrews turning in opposite directions. But in the extreme, compressed conditions of the early universe, or in the hearts of collapsed stars, the density of spinning matter could have been so immense that torsion played a dominant role. This leads to a stunning possibility. In standard general relativity, the equations inevitably lead to a singularity, a point of infinite density and zero volume at the beginning of the Big Bang and inside black holes. It is where our physics breaks down completely. Torsion offers an escape. As matter is crushed to incredible densities, the growing torsion field would generate a repulsive force, a kind of geometric back pressure that counteracts the crush of gravity. Instead of collapsing to an infinitely small point, the universe could have bounced from a previous state of contraction, or a black hole's core could reach a maximum density and then rebound. Torsion could erase the singularities from our cosmic map, replacing them with transformative events. Furthermore, some theorists propose that this twisting of spacetime in the early universe could have seeded structures that later evolved into the gravitational effects we attribute to dark matter. While not the mainstream view, the Einstein-Cartan theory has a dedicated following of physicists who see in its elegant geometry a more complete marriage between the quantum world of spin and the cosmic stage of gravity. It suggests that if we listen closely to the whispers of spinning particles, we might hear the faint, twisting melody of a spacetime that is far more intricate than we ever imagined. Spacetime's geometry may twist, but what about the shape of life itself? From the precise arrangement of a snowflake's arms to the instinctive flight pattern of a flock of starlings, nature displays an uncanny talent for organization. This leads us into a far more speculative realm, the theory of the morphogenetic field. Proposed by biologist Rupert Sheldrake, this is not a field of force or energy in the traditional physics sense. It is a hypothetical, non-physical field of information, a kind of invisible blueprint that guides the development and behavior of living systems. The word morphogenesis means the coming into being of form. How does a single fertilized egg cell containing identical DNA in every nucleus orchestrate itself to become a complex organism with a liver, a heart, and a brain all in the right places? Sheldrake suggested that beyond the chemical instructions in genes, there is a formative field, a pattern of habit shaped by the past forms of its species. Think of a crystal forming in a solution. The first time a new compound crystallizes, it might take time, its structure finding its way. But once that crystal pattern has formed somewhere in the world, subsequent crystallizations of the same compound seem to happen more easily, even in different laboratories. Sheldrake would argue this is morphic resonance, the influence of previous similar systems on later ones, as if the pattern, through repetition, strengthens its own morphogenetic field, making it easier to manifest again. This idea extends wildly into behavior. Consider a flock of hundreds of birds moving as one fluid entity, twisting and turning without a leader, or a colony of termites building a fantastically complex mound. Sheldrake proposes these are not just explained by simple rules, but are shaped by a collective field of habit, a resonance built from countless similar actions in the past. Even human learning could be touched by it. If many people learn a new skill or puzzle, like a video game level or a musical piece, does it become slightly easier for others to learn it later, anywhere in the world? This is the bold, controversial claim of morphic resonance, that patterns become more probable the more they are repeated. It is crucial to state that mainstream science roundly rejects this theory. Critics argue it is untestable in any rigorous way, that the phenomena it describes are fully explained by known chemistry, genetics, and emergent complexity. There is no accepted mechanism for such a field to operate or store information. Yet, its persistence in alternative thought speaks to a deep fascination. It attempts to answer the haunting question of where form and pattern come from, not just in matter, but in life and mind. It suggests a universe with a kind of memory, where habits crystallize not just in individual brains, but in the very fabric of reality, waiting to guide the next snowflake, the next flock, the next budding idea. While it stands far outside the fortress of established physics, it dares to propose that the hidden fields of our universe might not just push and pull, but also remember and teach. The idea of a universe with memory is poetic, but the bedrock of quantum mechanics presents us with a field of pure potential, one that is never still, not even in deathly cold and perfect darkness. This is the zero-point field, and it reveals that what we call empty space is the most vibrant thing in existence. According to the Heisenberg uncertainty principle, you can never precisely know both the position and the momentum of a particle at the same time. This is not a limit of our instruments, it is a fundamental rule of reality. Apply this principle to the quantum fields that fill the universe, and a staggering consequence emerges. Even at absolute zero, the temperature where all classical motion ceases, these fields cannot sit perfectly still. They must jitter, they must fluctuate. This ceaseless, unavoidable quantum jittering means that every cubic centimeter of the vacuum, the space between the stars and the air between your fingers, is a seething ocean of energy. It is not empty, it is full. This background hum of the universe is called zero-point energy. To visualize it, think of the static on an old television screen, that chaotic dance of black and white specks. Now, imagine that static is not on the screen, but is the screen itself, the fundamental canvas of reality. Within that noisy canvas, pairs of virtual particles and their antiparticles constantly wink into existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and vanishing back into the quantum foam. This is not just theory, we can see its effects. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, just nanometers apart. In that narrow gap, only certain wavelengths of the zero-point field's fluctuations can fit. Outside the plates, all wavelengths can exist. This creates a pressure difference, and the plates are pushed together by the sheer force of the vacuum outside. This is the Casimir effect, a measurable force caused by nothing but the restless energy of empty space. It has been confirmed in laboratories. Now the wild ideas begin. If the vacuum holds this immense energy, could we ever tap it? Could a spacecraft, for instance, somehow push against this quantum foam for propulsion, a concept sometimes called the quantum vacuum thruster? The challenges are beyond monumental, as this energy is everywhere and in every direction equally, making it like trying to sail by pushing against the ocean itself while you are submerged in it. But an even more profound idea links this field to the very nature of matter. A theory called stochastic electrodynamics proposes that what we perceive as inertia, an object's resistance to being pushed, is not an intrinsic property. Instead, it could be the result of the zero-point field. As an object accelerates, it plows through this quantum sea, and the field pushes back, creating the sensation of mass-resisting change. In this view, an object at rest is already in equilibrium with the field, but try to move it, and you feel the vacuum's drag. Some go further, suggesting that gravity itself could emerge from the interactions of matter with this energetic vacuum. While these are fringe ideas, they point to a breathtaking possibility. The solidity of your desk, the weight of your body, the very effort it takes to start moving might not come from you or the object at all. They could be an ongoing conversation with an invisible, infinite ocean of quantum motion, a hidden field whose constant whisper is the reason anything feels real at all. The zero-point field is a quantum sea of infinite potential, but it does not explain where the substance of the cosmos comes from. For most of the 20th century, a cosmic war raged over this very question. On one side stood the now dominant Big Bang theory, a universe with a fiery, singular beginning. On the other stood a brilliant and stubborn challenger, the steady-state model, championed by astronomer Fred Hoyle. His theory required a hidden field so radical it was named for its ultimate purpose, the creation field or C field. Hoyle's universe had no beginning and will have no end. It is eternal, existing forever in a state of perfect balance, but this presented an obvious problem. If space is expanding, stretching galaxies apart, the overall density of matter should continuously thin out, making the universe look different over time. The steady-state model demanded a universe that looks essentially the same everywhere and at every epoch, a principle called the perfect cosmological principle. To maintain this eternal sameness in an expanding cosmos, new matter had to appear out of nothing to fill the gaps. The C field was the proposed mechanism for this continuous creation. Imagine an expanding balloon with dots painted on it representing galaxies. As the balloon inflates, the dots move apart. In the Big Bang model, all the dots were painted on at the start. In Hoyle's model, there is no start. Instead, as the balloon stretches, new dots spontaneously form in the empty spaces between the old ones, maintaining a constant overall density. The C field was the brush that painted these new dots. It was a hypothetical field that, under the right conditions of extreme low density in the expanding voids between galaxies, would release tiny packets of energy that would condense into hydrogen atoms. The rate required was almost imperceptibly small, roughly 1 hydrogen atom per cubic meter every few billion years. This was not a dramatic explosion of creation, but a slow, steady trickle, a background hum of genesis keeping the cosmic engine running forever without a starter's pistol. The C field was a bold, elegant solution to preserve an eternal universe. It represented a profound philosophical stance that the cosmos is self-renewing and inherently stable. For a time, it was a serious contender supported by brilliant minds, but evidence began to mount against it. The discovery of quasars, incredibly bright and distant objects, showed the universe was different in the past, violating the perfect sameness principle. Then, in 1965, the cosmic microwave background radiation was discovered, the unmistakable afterglow of a hot, dense beginning. This was the death knell for the classic steady-state model. Yet, the C field's legacy is significant. It was one of the first serious attempts to use a dynamic hidden field to explain the large-scale structure and content of the cosmos from first principles. It forced cosmologists to think rigorously about alternatives and to seek definitive evidence. In a way, Hoyle's creative field finds a faint echo in our modern inflaton field, another hidden driver of cosmic genesis, though operating in a single, explosive burst rather than a perpetual whisper. The C field reminds us that the history of science is not a straight line to truth, but a branching tree of imagination where even the fallen branches shape the path of the trunk. It stands as a testament to human audacity, the idea that we could postulate a field whose sole job is to weave new atoms from the void, forever balancing the books of an infinite universe. Hoyle's creative field was an attempt to sustain eternity, but what if a hidden field could shatter time itself? This brings us to one of the most controversial ideas in theoretical physics, the tachyon field. Tachyons are purely hypothetical particles with one defining, impossible property: they always travel faster than light. In our universe, as an object with mass approaches light speed, its energy requirements become infinite, an unbreakable cosmic speed limit. Tachyons, by their very definition, would be born on the other side of that limit. They do not accelerate to faster than light speeds, they exist there permanently, and the closer they get to the speed of light from above, the more energy they lose. To make this bizarre concept mathematically possible, theorists assign tachyons an imaginary mass, a mathematical construct involving the square root of -1. This is not a physical substance you could weigh, but a formal trick that keeps the equations from breaking down. The consequences of such a field are staggering. According to the principles of relativity, anything moving faster than light could, from certain perspectives, be seen as traveling backward in time. This opens the door to severe causality violations. Imagine a tachyon signal being sent to your own past. You could receive a message warning you not to send the signal, creating a paradox where the message has no origin. The universe's logical consistency, the unbroken chain of cause and effect, would fray at the edges. Some theories suggest that if a tachyon field existed, it would be inherently unstable. Any disturbance would cause it to instantly decay, shedding energy until it settled into a stable state, perhaps even releasing the energy that triggered the Big Bang itself. This makes tachyons a fascinating, if unlikely, candidate for the inflaton field that drove cosmic inflation. For the most part, modern physicists view tachyons as mathematical curiosities rather than real entities. No experiment has ever detected a signal moving faster than light in a vacuum, and the causal paradoxes they introduce are deeply unpalatable to our understanding of reality. They often appear in equations as a sign that a theory has been pushed into an unstable, unphysical regime. Yet their allure persists. In science fiction, they are the perfect plot device for faster-than-light communication or time travel. In theoretical corners of physics, they occasionally resurface in discussions about the early universe's most extreme conditions or in certain string theory models. The tachyon field represents the outer boundary of what we are willing to entertain, a ghost in the mathematical machine reminding us that the cosmos might harbor rules even stranger than faster than light travel, rules that prevent such specters from ever stepping into the light of our reality. Tachyons flirt with breaking causality, but a more profound revolution suggests that reality itself might be a kind of illusion, a cosmic projection. This is the holographic principle, and it begins not with the whole universe but with the most enigmatic objects within it, black holes. In the 1970s, physicist Jacob Bekenstein made a startling calculation. He found that a black hole's entropy, a measure of its hidden information or disorder, is not proportional to its volume but to the surface area of its event horizon. This was bizarre. For any ordinary object like a book or a star, the amount of information it can contain grows with its volume. But a black hole, the ultimate consumer of information, seemed to store all the data about everything it swallowed on its two-dimensional surface. It was as if the three-dimensional interior was somehow encoded like a hologram on its two-dimensional boundary. A hologram is the perfect analogy. Look at the shiny, flat sticker on your credit card. It appears to be just a patterned, two-dimensional surface, but shine a laser through it and a stunning, three-dimensional image floats in space. All the information needed to reconstruct that 3D image is contained on the 2D film. The holographic principle boldly applies this logic to the entire cosmos. It proposes that all the information describing everything within a volume of space, every star, every planet, every particle, and every event, can be fully encoded on the lower dimensional boundary that surrounds it. For our universe, that boundary would be the cosmic horizon, the farthest limit of what we can ever see. This means the three-dimensional reality we experience, with all its depth and solidity, could be a magnificent projection from a vast, hidden field of information living on a distant, two-dimensional surface. The mathematics supporting this comes from string theory, in a formulation known as the AD-SCFT correspondence. It establishes a precise, equivalent dictionary between a theory of gravity operating in a certain kind of warped, higher-dimensional space and a quantum field theory without gravity operating on its lower dimensional boundary. In simpler terms, it shows that a universe with gravity can be perfectly described by a theory on its edge that has no gravity at all. The physics in the bulk, our world, is mirrored by the physics on the boundary. If this is true, then the forces and particles we perceive are not fundamental. They are emergent phenomena, like the temperature and pressure of a gas emerging from the collective motion of countless molecules. The solidity of your hand, the warmth of sunlight, the pull of gravity, all would be shadows cast by a deeper, flatter reality of pure information. We are not living in a universe but within a cosmic hologram with the true source code of existence written on the farthest walls of space. The implications are dizzying. It suggests a radical solution to the black hole information paradox, the question of whether information is truly destroyed when it falls in. In the holographic view, the information never enters the black hole in a 3D sense. It is painted onto the horizon, preserved forever. It also hints that the infinite density of the Big Bang singularity might be an artifact of our 3D perspective, a glitch in the projection, while the true description on the boundary remains smooth and well-behaved. While a full holographic description of our exact universe is still beyond reach, the principle stands as one of the most profound clues in the quest for quantum gravity. It tells us that if we want to understand the deepest hidden fields of our reality, we might need to stop looking inward into the volume of space and instead learn to read the whispers etched on its skin. The holographic universe paints reality as a grand illusion, but who is the dreamer? Beyond the fields of force and information lies the most intimate mystery of all, the nature of consciousness itself. For centuries, science has treated consciousness as an emergent property, a byproduct of complex biological computation in the brain. But this view runs into what philosophers call the hard problem. How can the swirling dance of neurons and neurotransmitters, the firing of electrical signals, give rise to the rich inner world of a sunset's color, the sting of grief, or the taste of chocolate? How does objective matter produce subjective experience? One radical answer, known as panpsychism, flips the script entirely. It proposes that consciousness is not something that emerges at the end of a long chain of complexity. Instead, it is fundamental, a basic property of the universe woven into the fabric of reality from the very beginning, as intrinsic as mass or charge. In this view, the cosmos is not just filled with fields of force, but with a field of experience. What if every particle, every ripple in the quantum foam, possesses some minute, elemental form of awareness? Not thought, not self-reflection, but a raw proto-consciousness, a bare whisper of isness. An electron would have a vanishingly simple experience, perhaps just the faintest sensation of its own existence and interaction. But when these particles combine into atoms, and atoms into molecules, and molecules into the unfathomably complex network of a human brain, these tiny whispers of experience could combine and integrate, amplifying into the symphony of thought, emotion, and sensation that is your mind. This is not suggesting rocks are thoughtful or planets are sad. It suggests that the ingredients for feeling are present in their most basic constituents, and complexity organizes them into what we recognize as a mind. The visual parallel is striking. Look at an image of a cosmic web of galaxies, vast filaments of light connecting shimmering nodes across billions of light years. Now look at a map of the human brain's neural network, a dense web of axons and dendrites connecting billions of neurons. The structures are eerily similar, one the architecture of the cosmos, the other the architecture of a mind. Could this be more than a beautiful coincidence? Could it be a hint that the universe is not just capable of producing consciousness, but is in some deep sense conscious itself, with our individual minds acting as localized knots of heightened awareness within a vast sentient field? This idea finds intriguing, though speculative, intersections with interpretations of quantum mechanics. The famous observer effect, where a particle's behavior seems to change when measured, has led some to ask if consciousness itself plays a role in collapsing quantum probabilities into definite reality. If consciousness is a fundamental field, then perhaps the act of observation is not a human privilege, but a fundamental interaction between this conscious field and the quantum fields, a dialogue that gives shape to existence. Panpsychism remains a philosophical theory far from scientific proof, yet it offers a profound shift in perspective. It suggests that the hidden fields of the universe are not cold, mechanical forces, but may contain the seeds of inner life. The quest to understand reality might not just be about mapping what is outside us, but about deciphering a universe that is, in its most fundamental essence, awake. If consciousness is a fundamental field, then time might be its most basic rhythm. We experience time as a smooth, continuous flow, an unbroken river carrying us from past to future. But what if this is an illusion of scale? Beneath our perception, time might not flow at all. It might tick. This leads us to the radical idea of the chronon field, the hypothesis that time itself is quantized. Just as matter is made of discrete atoms and light comes in packets called photons, time could be composed of indivisible chunks, the smallest possible unit of duration. This hypothetical quantum of time is called a chronon. It would be to a second what a single frame of film is to a full-length movie, the fundamental pixel in the animation of reality. The existence of such a unit would imply a background chronon field, a hidden structure that dictates the tempo of the universe, setting the beat for every event, every decay, every thought. The scale of this proposed unit is almost incomprehensibly tiny. Based on fundamental constants, its value would be the Planck time, approximately 10 to the negative 43 seconds. To put that in perspective, there are more chronons in a single second than there have been seconds since the Big Bang. Our brains, our clocks, our fastest computers all operate on timescales trillions of times coarser, which is why time feels so seamless to us. But at the most fundamental level, the universe might be a digital film advancing frame by frame. A discrete spacetime lattice where both space and time are granular could solve some of the most vexing infinities in physics. In theories of quantum gravity, when you try to calculate what happens at the center of a black hole or at the moment of the Big Bang, the math often blows up, predicting infinite density and curvature. These singularities are a sign that our theories are breaking down. If spacetime is pixelated, there is a smallest possible size and a shortest possible duration. You cannot squeeze matter into a volume smaller than a Planck length cubed, and you cannot measure a change faster than a Planck time. This natural cutoff would act like the resolution limit of a digital camera, preventing the equations from reaching true infinity. The chaos of a singularity would be replaced by the frenetic but finite dance of quantum geometry at the ultimate scale. Furthermore, a chronon field could offer a fresh perspective on the arrow of time, the mystery of why we remember the past but not the future. In a continuous universe, the laws of physics are mostly time-symmetric. They work the same running forward or backward. But if time is discrete, if the universe updates its state in chronon-sized steps, then each tick could involve an irreversible process, a tiny loss of information or increase in entropy that builds tick by tick into the one-way flow we experience. It would mean the forward march of time is not just a statistical effect of many particles, but is baked into the fundamental clockwork of existence. It is crucial to emphasize that this is wildly speculative. We have no experimental evidence for chronons, and many physicists believe time is an emergent property, not something to be quantized on its own. Yet the idea persists at the frontier of theoretical research, a tantalizing hint that the smooth fabric of spacetime might, upon closest inspection, reveal itself as the most intricate and delicate tapestry ever woven, its threads tied in knots of pure duration. The ticking of a chronon field is a whisper of structure, but the gravitational field can produce a roar so loud it shakes the cosmos itself. We have already heard it. Gravitational waves are not just a prediction of Einstein's theory, they are its most dramatic validation, proving that the gravitational field is not a static landscape but a dynamic, living fabric. These waves are literal ripples in spacetime, generated when massive objects accelerate violently, like two black holes locked in a final, deadly dance. For decades, this was pure theory. Then, on September 14, 2015, a signal arrived. It was not a flash of light or a burst of radio noise. It was a subtle, almost musical tremor in the detectors of the LIGO Observatory, two facilities in the United States separated by 3,000 kilometers, both registered an identical chirp. The data trace showed a classic pattern, a waveform that began with a slow, rising wobble and then rapidly crescendoed into a final, clean ring. It was the signature of two black holes, one about 36 times the mass of our Sun, the other 29, spiraling together at nearly half the speed of light. In a fraction of a second, they merged into a single, more massive black hole, and in that violent union, they radiated away energy equivalent to 3 solar masses, all in the form of gravitational waves. The event occurred over 1 billion light-years away, yet the ripple it produced stretched and squeezed the arms of LIGO L-shaped interferometers by a distance 10,000 times smaller than the width of a proton. That we can measure such an infinitesimal distortion is one of the greatest engineering feats in human history. This detection did more than confirm a century-old prediction. It opened an entirely new window on the universe, a sense beyond sight. Before LIGO, our view of the cosmos was based entirely on light, from radio waves to gamma rays. Now we can listen to the vibrations of spacetime itself. Each gravitational wave signal carries encoded information about its source. The frequency and amplitude of the chirp tell us the masses of the object. The shape of the ringdown reveals the properties of the final, merged object. We are not just detecting an event, we are forensically reconstructing it. Since that first detection, the LIGO and Virgo collaborations have catalogued dozens of these cosmic collisions, not just black holes but also neutron stars smashing together, events that also produce brilliant flashes of light observed by telescopes, truly marking the dawn of multi-messenger astronomy. But this is just the beginning of our listening. Current ground-based detectors like LIGO are sensitive to high-frequency waves, the shrieks and chirps from stellar mass collisions. To hear the deeper symphony of the cosmos, we must go to space. The Future Laser Interferometer Space Antenna, or LISA, will be a trio of satellites flying in a vast triangular formation, millions of kilometers apart. In the quiet vacuum of space, free from Earth seismic noise, LISA will tune into lower frequency gravitational waves. It will hear the steady hum of millions of binary white dwarf stars in our galaxy, a constant background chorus. It may detect the ripples from supermassive black holes merging at the hearts of distant galaxies, events that shake the entire cosmic web. Most tantalizingly, it might even hear the faint, primordial rumble from the first moments after the Big Bang, a gravitational wave background imprinted by cosmic inflation itself, the direct echo of the inflaton field's explosive decay. We are moving from hearing the occasional crash of cymbals to listening to the full orchestra of the universe, each instrument a different cataclysm, each note a ripple in the hidden tensor field that shapes our reality. The gravitational waves we listen for are ripples in a massless field, but what if some forces in the cosmos are carried by heavy messengers? This brings us to the vector field, a hidden architecture of a different kind. In physics, forces are often described by fields with a direction, a vector, like an arrow pointing somewhere. The photon field, which gives us light, is a massless vector field. Its ripples, photons, zip across the universe at light speed because they weigh nothing. But the equations allow for another possibility, a vector field with mass. This is described by the Proctor equations, and the particles it would produce are sometimes called Proctor bosons. A massive vector field would behave very differently. Its influence would be short-range because the mass of its carrier particle restricts how far it can travel before decaying. This is not a defect, it is a feature that could explain why we have never felt its touch. The most tantalizing candidate emerging from this idea is the dark photon. Imagine a shadowy twin to the ordinary photon. It would be similar, mediating a force, but with one crucial difference: it has a tiny amount of mass. This dark photon could be the hidden messenger for an entire dark sector, a whole shadow universe of dark matter particles that simply do not talk to our light and matter. In this scenario, dark matter would not be a single, inert substance. It could be complex, with its own atoms, chemistry, and forces, all interacting via these dark photons. Just as electrons interact by exchanging photons, dark matter particles could interact by exchanging dark photons, clumping and forming structures in ways that perfectly match the gravitational shadows we see in our cosmos. Finding such a field requires a detective's patience, looking for the tiniest cracks in the known laws. Since the dark photon would be a massive cousin to the ordinary photon, there is a slim chance the two could sometimes mix, like distant relatives recognizing a faint family resemblance. This mixing could allow an ordinary photon to occasionally convert into a dark photon, or vice versa. Experimenters are therefore searching for very specific anomalies. They look for electrons and positrons produced in particle collisions that seem to have a bit of missing energy and momentum. a signature that a dark photon might have been created and then swiftly decayed into invisible dark matter, carrying that energy away. Other experiments use powerful magnets and sensitive detectors to watch for electrons gaining a mysterious, tiny kick out of nowhere, which could be a sign of a dark photon from the cosmic background bumping into them. These hunts are happening at particle colliders, in underground laboratories shielded from cosmic rays, and even by reanalyzing data from decades-old experiments. It is a search for a ghost in the machine, a subtle deviation in a particle's path, or the energy balance of a collision that no standard process can explain. Each experiment is like tuning a radio to an unknown frequency, listening for a static whisper that could be the signal of a hidden force, a massive vector field quietly orchestrating a dark universe right alongside our own. If found, it would not just reveal a new particle, it would throw open the doors to an entire hidden cosmos, governed by its own rules and lit by its own dark light. Einstein's gravitational constant may not be written in stone. One of the most serious challenges to his theory of general relativity came not from a rejection of its brilliance, but from a simple, profound question. What if the strength of gravity is not a fixed number, but a changing whisper? This is the heart of the Brans-Dicke theory, which introduces a dynamic partnership between two hidden fields. In this framework, gravity is described not by the curvature of spacetime alone, but by a duo. The first is the familiar tensor field, the geometry of spacetime that warps and curves. The second is a new, universe-filling scalar field, a single number assigned to every point in space that dictates the local strength of the gravitational pull. Think of this scalar field as a cosmic dial for gravity's intensity. In regions where this field is stronger, gravity grips matter more fiercely. Where it is weaker, gravity's pull is more gentle. This dial is not set by a physicist's equation, but evolves dynamically, interacting with the distribution of matter and energy throughout the cosmos. The gravitational constant, big G, is not a fundamental constant of nature in this view. It is merely the current, local value of this ever-changing scalar field. This elegant idea was a direct precursor to concepts like quintessence, suggesting that the properties of the vacuum itself could evolve over cosmic time. But such a radical shift in gravity's nature would leave footprints, especially in our own celestial backyard. A dynamic gravitational strength would subtly alter the orbits of planets and the bending of starlight around the Sun. For instance, it could change the precise rate at which Mercury's orbit precesses, or affect how much light is deflected during a solar eclipse. For decades, these predictions put Brans-Dicke theory to the test. Scientists used radar beams bounced off planets and tracked the motion of spacecraft with exquisite precision. The result was a tightening noose of constraints. Any deviation from Einstein's predictions was smaller than the most sensitive instruments could detect. The scalar field, if it exists, must be incredibly stiff, barely budging in response to the matter in our solar system. Its dial is effectively frozen in place, making it indistinguishable from a true constant in our local observations. This does not kill the theory, but it forces it into a corner where it looks almost exactly like general relativity in the present era. Yet its historical role is monumental. It was the first robust, mathematically consistent alternative to Einstein's masterpiece, proving that other descriptions of gravity were possible. It expanded the imagination of physicists, teaching them to consider gravity not as a monolithic force, but as a potential conversation between fields. This opened the door for the inflationary and dark energy models that followed, where scalar fields drive the evolution of the entire universe. Brans-Dicke stands as a crucial stepping stone, a reminder that even our most cherished constants might be the quiet, dynamic voices of hidden fields, their changes so slow we have yet to hear them turn. The universe's hidden fields may not be confined to the cosmos of stars and atoms. For centuries, across countless cultures, another layer of reality has been described, one that clings not to space but to life itself. This is the theory of the bioplasmic field, a concept from the fringes of parapsychology that proposes every living organism is enveloped in a subtle, luminous energy body. Often called an aura or a psi field, it is imagined as a shimmering sheath of colored light, a hidden field of vital force that reflects our health, emotions, and even our thoughts. In this view, the physical body is just the densest manifestation of a more fundamental energy template, a blueprint of light that guides growth and healing. Proponents suggest that gifted individuals, or those using special photographic techniques like Kirlian photography, can perceive or capture this radiant halo, seeing disruptions in its flow as precursors to physical illness or emotional distress. The field is also frequently linked to purported psychic phenomena, acting as the medium for telepathy, where minds communicate through ripples in this shared energy sea, or for psychokinesis, where the will directly influences the physical world by manipulating this personal field of force. It is a deeply romantic idea that we are all connected by a web of living light, our inner states painted in colors only the sensitive can see. Yet, it is crucial to state with absolute clarity that mainstream science finds no credible evidence for such a field. No instrument under controlled, repeatable conditions has detected an energy body independent of known electromagnetic and biochemical processes. What Kirlian photography typically captures are corona discharges influenced by moisture and pressure, not a secret life force. The phenomena of telepathy and psychokinesis have never been reliably demonstrated in rigorous laboratory settings that rule out fraud, coincidence, or sensory leakage. So why include it in a list of cosmic theories? Because the bioplasmic field represents a powerful and enduring human impulse, a cultural and historical example of the hidden field concept applied to the greatest mystery of all, consciousness itself. Long before quantum field theory, humans intuited that reality might be filled with invisible forces connecting mind and matter. This idea speaks to a deep desire to see our inner lives reflected in the fabric of the universe, to be more than just biological machines. It is a testament to the imagination's relentless drive to map the unseen, even when it ventures far beyond the borders of established evidence. While it remains in the realm of myth and mystery, it echoes a question that even the hardest sciences grapple with: where in the architecture of reality does the vivid theater of our experience truly reside? The bioplasmic field is a human dream of connection, but physics pursues a dream of ultimate unity. For over a century, a single, elegant idea has captivated the greatest scientific minds: the quest for a theory of everything. The goal is breathtakingly simple: to describe all the forces of nature, from the gravity that binds galaxies to the nuclear forces inside atoms, as different vibrations of a single, fundamental entity, the unified field. Imagine if every note in a symphony, from the deepest bass to the highest violin, was produced by the same vibrating string, simply by playing it in different ways. That is the grand ambition: to find the cosmic instrument whose harmonies compose reality itself. The leading candidate for this ultimate theory is superstring theory. It proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. Their different vibrational patterns, like different notes on a guitar string, give rise to every particle and force we know. An electron is one note. A quark is another, a photon is yet another. Even the graviton, the hypothetical carrier of gravity, emerges naturally from this vibrational symphony, offering a potential path to unite gravity with quantum mechanics. But this elegant idea comes with a cosmic price: extra dimensions. For the mathematics of string theory to work consistently, the universe must have more than the 3 dimensions of space and 1 of time we experience. It requires 10 dimensions, so where are the other 6? Theorists propose they are curled up or compactified into shapes so incredibly small at the Planck scale that they are forever hidden from our perception. The geometry of these extra dimensions is not arbitrary. They are described by intricate, beautiful shapes known as Calabi-Yau manifolds. Picture a 6-dimensional labyrinth of twisting, looping space, a shape of stunning complexity. The specific way these dimensions are curled determines the properties of the universe they produce, the masses of particles, the strengths of forces, even the number of generations of matter. And here lies a staggering, almost humbling revelation. There is not just one way to curl these dimensions. The number of mathematically possible Calabi-Yau shapes, each representing a different possible vacuum state for the cosmos, is estimated to be around 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it exceeds the count of atoms in the observable universe. This is the string theory landscape, a cosmic multiverse of possibilities, where every possible configuration of hidden fields and physical laws exists somewhere in a greater meta-reality. Our universe, with its specific Higgs field, its particular dark energy, and its exact set of particle masses, would be just one accidental garden in an infinite wilderness of physics. This idea was expanded further by a proposal known as M-theory, which suggests that the various string theories are all different facets of a single, deeper theory existing in 11 dimensions. In this vision, the fundamental objects are not just one-dimensional strings, but also higher-dimensional membranes, or branes for short. Our entire three-dimensional universe could be a vast, floating brane drifting within a higher-dimensional bulk space, with gravity perhaps leaking into our world from this greater arena. The unified field, therefore, may not be a single equation on a page, but an almost living, breathing geometry in a hidden dimensional space, its vibrations weaving the tapestry of all that is. The pursuit of this theory represents the pinnacle of human intellectual ambition, a search for a single source of all complexity. Yet it also confronts us with a profound philosophical question. If the ultimate laws reside in a landscape of near-infinite possibilities, does that mean our particular universe and our existence within it is ultimately a cosmic accident, one beautiful but random tune plucked from an endless symphony of silence? This beautiful but accidental universe rests on a foundation that may not be as solid as it seems. Our cosmic home could be perched on the edge of a cliff, held in place by a precarious balance of energy. This is the theory of the false vacuum, and it suggests our entire reality is living on borrowed time. It all comes back to the Higgs field, that cosmic molasses that gives particles mass. After its discovery, physicists ran the equations to understand its properties at the highest energies. The results were unsettling. The Higgs field might not be sitting in its true, lowest possible energy state. Instead, it could be trapped in a false vacuum. Imagine a ball resting in a small dip on the side of a steep mountain. The ball is stable for now, it is not rolling. But this position is not the absolute bottom of the mountain. Far below, there is a much deeper, more stable valley, the true vacuum. The ball in the dip represents our universe existing in a state of false stability. For billions of years, it has sat there, seemingly secure. But quantum mechanics introduces a terrifying possibility: quantum tunneling. There is a tiny, non-zero probability that the ball could spontaneously tunnel right through the mountain wall and appear in that deeper valley without having to roll over the top. In cosmic terms, a random quantum fluctuation somewhere in space could cause the Higgs field in that region to tunnel into its true, lowest energy state. This would not be a gentle transition, it would be catastrophic. The moment this tunneling event occurs, it creates a microscopic bubble of true vacuum. The laws of physics inside this bubble are completely different. The Higgs field has a new value, which means the masses of fundamental particles, the strength of forces, even the nature of chemistry itself are rewritten. This new state is more stable, and it exerts an irresistible pressure on the unstable false vacuum surrounding it. The bubble begins to expand in all directions, not at the speed of sound or rocket travel, but at the speed of light. Its wall is a sphere of fundamental transformation, a wave of new physics racing outward. As it expands, any structure it encounters is instantly and utterly erased. Galaxies, stars, planets, atoms, they are not just destroyed, they are unmade. The very particles that constitute matter cease to exist in their familiar forms, reconfigured into something alien according to the new, true vacuum rules. From our perspective, there would be no warning. One moment, the universe is as it always was. The next, an invisible sphere of annihilation, already light years across, touches our corner of space. In an instant, everything you know, every memory, every structure in the cosmos vanishes without a trace, replaced by a new reality with laws we cannot predict. The entire observable universe could be consumed in a cosmic blink. Is this our future? Calculations based on the measured mass of the Higgs boson suggest our vacuum might indeed be metastable, a temporary resting place. The good news is that the probability of such a tunneling event occurring in any given region of space-time is astronomically small, likely requiring more time than the current age of the universe many times over. We are probably safe for trillions of years, yet the mere possibility is a humbling reminder. The hidden fields that dictate our reality may not have settled into their final, eternal form. We may be living in a beautiful but ultimately temporary configuration of the cosmos, a delicate bubble of specific laws waiting to pop. The false vacuum is a chilling vision of cosmic fragility, but quantum mechanics presents us with a daily dose of profound uncertainty. In the standard Copenhagen interpretation, a particle like an electron does not have a definite position until we look at it. It exists as a cloud of probability, a wave of potential, and the act of measurement forces it to randomly choose a specific location, collapsing the wave function. This inherent randomness, this dice roll at the heart of reality, troubled many great physicists, including Albert Einstein, who famously declared that God does not play dice. What if he was right? What if the dice are loaded by a hidden hand? This brings us to a fascinating alternative, Bohmian mechanics, and its central entity, the pilot wave field. In this interpretation, particles are not ghostly probability clouds. They are real, tiny, point-like objects with definite positions and trajectories at all times, even when we are not looking. They always know exactly where they are. So what creates the bizarre wave-like behavior, the interference patterns in the famous double-slit experiment? The answer is a second, hidden reality, a guiding wave that fills all of space, the pilot wave field. Think of a surfer riding a powerful ocean wave. The surfer is the particle, a solid object with a specific location on his board. The wave he rides is the pilot wave, a vast, undulating field that carries information about the entire environment. The surfer does not control the wave, he is guided by it. His path is completely determined by the shape and force of the wave beneath him. In Bohmian mechanics, every particle is such a surfer. The pilot wave field, calculated from the universal wave function, contains information about every slit, every barrier, every other particle in the experiment. It is this non-local field that tells the particle exactly where to go. In the double-slit experiment, the electron particle passes through only one slit, but its guiding pilot wave passes through both. The wave interferes with itself on the other side, creating a complex pattern of ripples. The particle, surfing this intricate pattern, is steered along a very specific path that ends up clustering with other particles at the bright bands of the interference pattern, never the dark bands. The randomness is an illusion. Given the same initial conditions and the same pilot wave, the particle would follow the exact same path every single time. This hidden field solves another quantum mystery in a strikingly direct way: entanglement. When two particles become entangled, their guiding pilot waves become inextricably linked, forming a single, unified field. Even if the particles are separated by light years, this non-local connection in the pilot wave field remains instantaneous. A measurement on one particle updates the entire guiding wave, which immediately informs the trajectory of its distant partner. There is no spooky action at a distance, just a single, interconnected field updating itself everywhere at once. So why is this elegant, deterministic picture not the mainstream view? The primary objection is its need for non-locality, this instant connection across space, which seems to conflict with the spirit of relativity, even if it does not technically violate it by transmitting information faster than light. Critics also point out that the pilot wave field feels like an added layer of complexity, a hidden machinery that produces the same statistical predictions as the simpler, if more mysterious, Copenhagen interpretation. It is a matter of philosophical taste, a choice between a universe of fundamental randomness and one of hidden determinism. Yet, Bohmian mechanics stands as a powerful testament to the fact that our quantum story is not yet fully written. It offers a vision of a cosmos where every particle, from an electron in a lab to a photon from a distant quasar, is on a precise, preordained journey, silently guided by an ocean of invisible waves, a hidden field charting every course through the quantum sea. The deterministic world of pilot waves offers a clean, if hidden, logic, but some theories venture into far murkier waters, where the fabric of physics blurs with the mystery of mind. This brings us to a deeply speculative leap, a fringe idea that attempts to bridge the Einstein-Cartan torsion field with the phenomenon of consciousness itself. Recall that in Einstein-Cartan theory, spacetime is not just curved by mass, but twisted by the intrinsic spin of elementary particles. This torsion is a geometric memory of quantum spin etched into the cosmos. Now take this concept and bring it into the most complex system we know, the human brain. Within your skull, billions of neurons are constantly firing. This electrical activity is fundamentally the motion of electrons, and every electron carries spin. In this speculative view, the sheer density and orchestrated motion of these spinning particles within neural networks could generate a localized dynamic torsion field, a subtle twisting of spacetime at the microscopic level around and within the brain. This is not a field of force in the traditional sense, but a field of geometric information, a pattern of twists and turns that mirrors the patterns of neural activation. Proponents of this idea suggest this biological torsion field could do more than just exist. It could interact. The spin states of electrons in one neuron might influence, through this shared geometric torsion, the spin states in another, providing a potential non-electrochemical channel for information processing. Could this twisting of spacetime geometry be a physical substrate for the binding of disparate sensory inputs into a single, unified experience? Could the elusive neural correlate of consciousness be found not just in the firing of neurons, but in the specific dynamic torsion pattern their collective spin generates in the fabric of reality itself? It is a staggering proposition that your thoughts and feelings might not just be represented by, but might actually be, a unique dance of spacetime twists. This speculation naturally expands into even more unconventional domains, suggesting that such a personal torsion field might not vanish at death, but could linger as a faint geometric imprint, a ghostly twist in space, which some interpret as the basis for spiritual concepts of an energy body or soul. It is crucial to understand this stands far outside mainstream science. There is no empirical evidence that torsion fields operate at biological scales or that they have any connection to cognition. It is a hypothesis that lives at the wild intersection of theoretical physics and metaphysics, a testament to how ideas about hidden fields often overflow their original containers. When we stare into the profound unknowns of consciousness and the deep structure of reality, the human imagination instinctively tries to build bridges using whatever tools, torsion, spin, geometry it can find. These speculative leaps, while scientifically unproven, highlight a beautiful and relentless drive. They represent our attempt to see the swirling neural galaxy of the brain and the twisting geometry of spacetime not as separate realms, but as two expressions of a single, hidden symphony, where the music of matter and the experience of mind might finally share a common, vibrating source. Our reality might be a solitary island in a far vaster sea. The idea of a unified field in higher dimensions leads to a breathtaking cosmic vision, where our entire universe is not the whole story, but merely a three-dimensional membrane or brain adrift within a grander, hidden expanse. This is the brain world scenario, and the hidden fields within it rewrite our origin story. Imagine our cosmos as a vast, impossibly thin sheet, like a single page of an infinite book. This page has three dimensions of space, the length, width, and depth we experience, but this page exists within a higher dimensional volume called the bulk. Other pages, other brains, could be floating parallel to ours in this bulk, each potentially hosting its own entire universe with different physical laws, forever separated by a gap we cannot cross. In this picture, many of the forces and particles we know, like the electromagnetic force, are like ink trapped on the page. Their fields are confined to our brain, which is why we only perceive three spatial dimensions. But gravity is different. It is the force of the bulk itself. It can leak off our brain, spreading into the higher dimensions. This could explain why gravity is so astonishingly weak compared to the other forces. Its strength is not feeble, it is simply diluted, its influence spreading out into unseen directions we cannot access. This elegantly solves a major hierarchy problem in physics, the puzzle of why gravity is 10 to the power of 36 times weaker than the electromagnetic force. The force isn't weak, we are only feeling a fraction of its true strength. This leads to a radical new genesis. What if the Big Bang was not a singular eruption from nothing, but a colossal collision? This is the ekpyrotic model from the Greek word for conflagration. In this scenario, our brain and a parallel brain float quietly in the bulk, drawn together by a gentle force across the gap. They move slowly, then faster, until they slam into each other. The impact is not a destructive crash, but a transformative one. The immense kinetic energy of the collision is converted into heat, radiation, and matter, flooding our brain with the seething, dense plasma of a new beginning. What we call the Big Bang is the fiery aftermath of that contact. The universe begins hot and expanding, not from a point but from a state of violent, planar contact. This model provides a compelling alternative to cosmic inflation. The slow, steady approach of the brains before the collision would naturally stretch and flatten any pre-existing wrinkles, solving the horizon and flatness problems just as inflation does, but through a cyclic, mechanical process. After the collision, the brains bounce apart, each now filled with a new, hot universe. They then drift, cool, and expand until the attraction pulls them back for another collision in a cycle potentially repeating forever. Our entire cosmic history, from the first light to the last star, could be just one phase in an endless cosmic rhythm of approach, collision, and rebirth. The hidden fields here are of two kinds, those stuck to our brain that define our physics, and those that live in the bulk like gravity, whose true nature is forever beyond our full perception. We are left with a humbling and magnificent possibility. The galaxies we see are not the remnants of an explosion from nothing, but the shimmering aftermath of a touch, a cosmic kiss between worlds we will never see, echoing in the expanding light of everything we know. The brain world's cosmic collisions are a modern echo of a much older idea, one that was once the cornerstone of physics before being spectacularly overthrown. For centuries, scientists believed space was not empty, but filled with an invisible, weightless, and frictionless substance called the luminiferous ether. This ether was thought to be the absolute, unmoving stage upon which the universe played out, and more importantly, the medium through which light waves traveled, just as sound waves need air. It was a beautiful, logical concept. If light was a wave, it needed something to wave in. The ether was that something, a hidden field before we had the word field. To prove its existence, physicists Albert Michelson and Edward Morley designed an exquisitely sensitive experiment in 1887. They reasoned that as Earth hurtled through this stationary ether sea, it should create an ether wind, just as a moving car creates a wind. Their apparatus split a beam of light, sending the parts on perpendicular journeys before recombining them. If an ether wind existed, it should slow one light beam relative to the other, creating a telltale interference pattern shift as they rotated the device. The result was a shock that reverberated through science. They found nothing, no shift, no wind. The speed of light was constant in every direction, regardless of Earth's motion. This null result was the first crack in the classical worldview, a direct path to Einstein's theory of special relativity, which boldly declared there was no absolute rest frame, no ether. The concept was publicly buried, a cautionary tale of a beautiful idea slain by an ugly fact, but the ghost of the ether never truly left the building. It has been reborn not as a material substance, but in the form of the very hidden fields we have been exploring. The quantum vacuum is the modern ether. It is not a stationary fluid, but a seething, energetic substrate that fills all of space, a background entity that defines the rules. The Higgs field is a modern ether. It is an omnipresent molasses that imparts mass to particles, a property once thought to be intrinsic to matter itself. Even spacetime in general relativity is a modern ether. It is a dynamic, flexible fabric that can be curved and rippled, providing the stage for all events and defining the ultimate speed limit for light. Not because light is waving in it, but because its geometry is the arena of causality. The key difference is profound. The old ether was an absolute reference frame, a preferred state of rest. Our new ethers are not. They are local and democratic. The value of the Higgs field is the same for an observer moving at near light speed as it is for one at rest. The quantum vacuum looks the same from all inertial frames. They are background entities that respect the laws of relativity while still providing the medium that gives particles their properties. This is the fascinating evolution of a scientific idea. We did not simply discard the ether. We refined it, transformed it, and gave it a precise mathematical language. The haunting etchings of the Michelson-Morley apparatus with its delicate mirrors and hopeful beams were not a dead end. They were the first clumsy attempt to measure the hidden architecture of the vacuum. Today, our tools are particle colliders and gravitational wave observatories, but the quest is the same, to understand the silent, unseen something that fills the void and writes the laws of reality. The ether did not die, it simply changed its name, and in doing so became infinitely more strange and wonderful. From the ashes of the old ether, new fields of meaning emerge. Beyond the equations of physics and the chemistry of the brain, some thinkers propose a hidden layer of reality that is not about force or energy, but about significance itself. This is the theory of the noetic field, a speculative concept from the crossroads of philosophy, consciousness studies, and theoretical science. The word noetic comes from the Greek nous, meaning mind or intellect. A noetic field would be a fundamental, universe-wide field of information, meaning, or conscious potential. It is not a field that pushes particles around. Instead, it is a field that informs existence, a hidden landscape of potential patterns and understandings that the physical world expresses. In this view, the universe is not a blind machine. It is more like a vast, evolving idea. The laws of physics, the constants of nature, the very structure of matter could be stable, recurring patterns within this deeper field of noetic information. They are not arbitrary rules, but meaningful forms that have crystallized from a sea of potential meaning. This leads to a profound shift in the relationship between consciousness and cosmos. Instead of consciousness being a late-arriving accident in a mindless universe, consciousness becomes a primary feature, a way the noetic field becomes aware of itself. Your mind, your thoughts, your moments of insight are not locked inside your skull. They are localized accesses, focal points where this universal field of meaning becomes self-reflective. Think of a calm lake reflecting the sky. The sky is the noetic field, the vast expanse of potential meaning. Your conscious mind is not the lake itself, but a specific, still point on its surface where a perfect, clear reflection can form. The ripples of your thoughts are disturbances in that local clarity, but the source of the image is the entire sky. This connects to the idea of a participatory universe, famously explored by physicist John Archibald Wheeler. He suggested that we live in a cosmos where the act of observation is not a passive recording, but an active act of creation. In the quantum realm, a particle's properties are not fixed until measured. Wheeler took this further, proposing that the universe only comes into definite existence through the acts of observation made by conscious beings throughout its history. The noetic field provides a potential medium for this participation. Our observations, our questions, are not separate from the cosmos. They are interactions with this foundational field of information, calls that elicit specific responses from the quantum fog, gradually building a coherent reality through a grand cosmic dialogue. It is as if the universe is a story waiting to be read, and every conscious glance is a sentence being written into being. How would we ever test such an abstract idea? Proponents point to phenomena that defy easy material explanation, like moments of profound intuition, spontaneous healing, or the seemingly synchronous events Carl Jung called synchronicity, meaningful coincidences that feel charged with significance. These, they argue, might be glimpses of the noetic field in action, moments where the boundary between personal mind and cosmic information briefly softens, allowing a transfer of meaning that bypasses normal cause and effect. This is without question the farthest frontier of hidden field thinking. It exists in a space between established science and metaphysical philosophy, a testament to the human drive to find unity not just between forces but between matter and mind. While it offers no equations for a particle collider, it poses the ultimate question. Could it be that the deepest hidden field, the final substrate of all that is not a vibration in 10 dimensions or a ripple in spacetime, but a silent, waiting ocean of understanding, and we are its fleeting, wandering thoughts? Phantom energy is the dark side of quintessence, a hidden field so voracious it would devour the cosmos from within. While ordinary dark energy pushes space apart at an accelerating rate, a phantom field would push harder, its repulsive power growing stronger as the universe expands. This is not just an acceleration, it is a runaway feedback loop with a terrifying endgame, the Big Rip. The key lies in a simple number physicists call the equation of state, which describes the pressure a dark energy field exerts relative to its energy density. For a simple cosmological constant, this number is exactly -1. For quintessence, it can vary but typically stays close to that value. A phantom field, however, has a value less than -1, a subtle mathematical difference with apocalyptic consequences. It means the field's energy density does not dilute as space expands, it actually increases. The more the universe stretches, the stronger this phantom field becomes, and the stronger it becomes, the faster it stretches the universe in a vicious cycle that culminates in a finite, calculable moment. Imagine a rubber band being pulled apart. At first, it stretches with steady resistance. That is our current acceleration. But a phantom field is like a rubber band that gets easier to stretch the more you pull it, until your hands are flying apart uncontrollably. In cosmic terms, the repulsive gravity of this field would eventually overwhelm every force that holds structures together, not just the gentle tug between galaxies, but the very bonds of matter itself. The end would come in stages, a cosmic demolition from the largest scales to the smallest. First, the phantom energy's grip would overcome the gravitational glue of galaxy clusters, flinging these island universes apart into the endless dark. Next, the gravity binding individual galaxies would fail. Stars would be ripped from their orbits and hurled into the void, their light fading into isolation. Then, as the phantom field's power intensified further, it would turn on solar systems. Planets would be torn from their stars. Later, the stars and planets themselves would be shredded, their material pulled apart by a force stronger than their own gravity. In the final moments, before the very fabric of spacetime is potentially torn asunder, the phantom field would attack the building blocks of reality. The electromagnetic force holding atoms together would be overcome, tearing electrons from nuclei. Then, even the mighty strong nuclear force which binds atomic nuclei would falter. Protons and neutrons would be ripped apart, and quarks would be scattered into the expanding nothingness. The universe would end not with a whimper or even a bang, but with a silent, infinite scream as every structure, every particle, every trace of order is dissolved into a thin, featureless haze. Could such a monstrous field truly exist? Current observations of the cosmic expansion, from supernova to the cosmic microwave background, constrain the dark energy equation of state to be very close to -1. The data allows for a slight possibility that it could dip into the phantom regime, but just barely. The universe, for now, seems to be holding this phantom at bay. Yet the theoretical possibility remains a profound warning from the mathematics. It tells us that the vacuum of space and the hidden fields that define it are not necessarily benign or stable. A tiny shift in the properties of a universe-wide field could unlock a latent instability, a self-feeding frenzy that would erase all we know. The phantom field is the ultimate embodiment of cosmic fragility, a reminder that the forces weaving our reality together might one day decide to unravel it stitch by fundamental stitch. The relentless expansion of phantom energy would erase all structure, but it operates within a universe that already possesses a deep, fundamental bias. Everything flows in one direction from past to future. We remember yesterday but not tomorrow. A shattered glass does not reassemble itself. This is the arrow of time, the most familiar yet profound mystery in all of physics. Why does time have a direction at all? The laws of physics, from Newton to quantum mechanics, are mostly time-symmetric. They work just as well running backward as forward. So why does our reality feel so lopsided? The classic answer lies in entropy, the measure of disorder in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. A drop of ink disperses in water, smoke billows from a fire, a hot cup of coffee cools to room temperature. These are all journeys from order to disorder, and they define our psychological arrow of time. We remember the ordered past and move toward the disordered future, but this just pushes the question back one step. Why was the entropy of the universe so incredibly low in the first place? Why did our cosmos begin in a state of exquisite, improbable order? This is where hidden fields might hold the key. Some theorists suggest that the arrow of time is not an emergent property, but a fundamental one, imprinted by a primordial field at the birth of everything. Imagine a universe-filling field that, like a compass needle, had a specific orientation set at the moment of creation. This field's value would point in one temporal direction, defining a universal past and future from the outset. This cosmic pointer could have been set by the very act of cosmic inflation. As the inflaton field decayed and reheated the universe, it may have done so in a way that was inherently asymmetric, like a clock being wound in one direction only. That single, irreversible event could have biased the entire subsequent evolution of the cosmos, ensuring that entropy would forever increase from that point onward. Another possibility ties the arrow to the boundaries of reality itself. In the holographic principle, our three-dimensional universe is a projection from a two-dimensional boundary. The laws on that boundary are timeless, but when you project them into our volumetric world, that translation process might naturally introduce a direction, like reading a story from the first page to the last. The flow of information from the boundary into the bulk could be what we experience as the forward march of time. This means the arrow is not in the events themselves, but in how the cosmic code is rendered into existence. There is an even more speculative idea that the arrow is maintained by a continuous, subtle field that interacts with quantum systems. Every time a quantum probability wave collapses into a definite outcome, that collapse is irreversible. It adds a tiny bit of entropy to the universe's ledger. This could be driven by a background field that gently nudges quantum systems toward decoherence, constantly resolving maybe into is, and in doing so, ratcheting time forward one click at a time. Your consciousness, which relies on these irreversible neural processes, would be swept along in this current. So, the reason you cannot remember tomorrow is not just a quirk of your brain's biology. It may be woven into the deepest fabric of the cosmos, a silent, one-way field set in motion at the first instant, guiding the universe from a state of pristine order toward an eventual cold equilibrium. The flow of time might not be an illusion or an emergent property. It could be the most fundamental hidden field of all, the invisible river in which every galaxy, every atom, and every thought is carried forever away from the singular moment of its source. The relentless flow of time carves a single path from the past, but what if every possible path is taken? Our final hidden field is not one of force or substance, but of pure potential. It is the universal wave function, and according to the many worlds interpretation, it is the only thing that truly exists. This is not a theory of multiple, separate universes colliding in a void. It is the vision of a single, unimaginably vast quantum field, a field of all possibilities that constantly and quietly branches. Every time a quantum system faces a choice, every time an electron could spin up or down, a photon could be reflected or transmitted, or a radioactive atom could decay or not, the entire wave function does not collapse into one outcome. It splits, both possibilities become real, but they become real in newly branched, non-communicating strands of the same overarching reality. Imagine a single, mighty river flowing through a canyon. At a certain point, the river reaches a rock. In our everyday experience, the water seems to choose one side to flow around, but in the many worlds view, the river does not choose. The entire canyon splits, the rock duplicates, and the river flows down both newly created channels simultaneously. Each branch is equally real, a full-fledged universe with its own consistent history. But from that moment forward, the branches are forever separate, their inhabitants unaware of the other stream. This means the cosmic wave function, this ultimate field of possibility, contains within it every event that could possibly happen somewhere on its infinite fractal tree. There is a branch where you turned left instead of right this morning. There is a branch where the dinosaurs never went extinct. There is a branch where every coin flip in history came up tails, and another where they all came up heads. Every possible configuration of matter, every possible life story, every imaginable variation of physical law that is logically consistent is realized in some branch of this unending cascade. The implications for identity are dizzying. You are not a single continuous self, you are a branching entity. At this very moment, with every quantum fluctuation in your brain, countless versions of you are diverging, each embarking on a slightly different future, each convinced they are the only one. The version of you hearing these words is just one thread in a tapestry of near infinite breadth. This resolves the strangeness of quantum measurement without any collapse or observers. There is no dice roll because every number comes up. The wave function never collapses, it just eternally evolves, and we, as conscious beings, are swept along one specific branch, forever unaware of the others. We do not experience the splitting, we only experience the single, linear history of the branch we are on. The many worlds field is the ultimate hidden architecture, a cosmos where nothing is ever lost, no possibility is ever discarded. Every dream, every fear, every road not taken is lived out in full somewhere on the tree. It is a universe of absolute determinism and infinite diversity, all contained within a single, silent, and endlessly dividing quantum wave. It suggests that the deepest truth of reality is not a collection of things, but a shimmering spectrum of maybes, forever crystallizing into an infinity of nows. From the Higgs field giving mass to reality to the quantum wave function spawning infinite worlds, we have journeyed across the hidden architecture of everything. 30 theories, each a different lens on the cosmos, from the firmly proven to the wildly speculative. We have seen fields that twist spacetime, fields that remember habits, fields that might be conscious, and fields that could one day unravel existence itself. This is not just a catalogue of ideas, it is a map of human curiosity, a testament to our refusal to accept the surface of things. The search for these hidden fields is the most profound quest we can undertake. It is the search for the source code of reality, the invisible lines of force and information that write the laws of physics, sculpt galaxies, and spark the flame of consciousness in the dark. Every experiment, from the colossal colliders to the silent listening posts in space, is an attempt to read the whispers of this deeper reality. We are learning that the universe is not a collection of isolated objects, but a conversation between layers, a symphony played on instruments we are only beginning to hear. So remember, the next time you look up at the night sky, you are not just seeing points of light in a void. You are gazing at the magnificent, visible tip of an iceberg, whose true substance lies in the churning, invisible depths below. The universe is not just stranger than we imagine, but perhaps stranger than we can imagine. Which of these hidden fields resonates most with you? Was it the cosmic molasses of the Higgs, the phantom menace of dark energy, or the infinite branches of the many worlds wave? Share your favorite theory in the comments below. If you enjoyed this deep dive into cosmic mysteries, subscribe and turn on notifications for more journeys to the edge of understanding. Keep questioning, keep wondering, and never stop